Hello everyone, in this lecture we will be learning about the transient response of CMOS circuit. In the earlier lecture we have learned about DC analysis. In DC analysis tells us the output voltage where the input voltage is constant. But in transient analysis neither the input nor the output voltage is constant. We see that both the voltage changes with time and it shows the response of input and output with respect to time. And it requires, since it shows the output with respect to time, it requires solving differential equations. Input is usually considered to be a step or ramp, that is input increases from 0 to VDD either abruptly or in a definite time t. Let us look at the step response of an inverter. Now, what is step response? Step response means that the input voltage will suddenly rise from level 0 to level 1. And what is the change in the output voltage? That thing we will observe. Now, so we are expressing the step response Vin is equal to U t minus t naught VDD. Here U t minus t naught means a unit step. Unit step means it rises from 0 to 1 at a time t naught. And before the input rises to VDD, the output voltage is supposed to be VDD because at that moment input voltage is supposed to be 0. And after the input voltage rises to VDD, we have to see how the output voltage behaves with respect to time. Now, in the output is connected, we are considering output is connected to a capacitor or its capacity with a load C load. Now we know I is equal to C dV dt. Again, we see that the voltage at the output is decreasing, so dV dt will be negative. So that negative sign, if we consider the negative sign here, we get dV dt is equal to minus IDSN divided by C load. Here the current IDSN is the current passing from drain to source of the NMOS. So as a result, we can see that the nature of the output is gradually decreasing and it depends on the factor time. Now, this current can be modeled in different ways. We have already learned about Shockley equations. These are the Shockley equations. This is for cutoff, this is for saturation, and this is for linear region. We can model the currents in this way. Now, when we are considering delays, that is the dependence of time, we have to consider. We have several parameters or definitions which we must follow. Firstly, TPDR, rising propagation delay. It is defined as when the 50% value of input, the time difference between the 50% value of input and the 50% value of output. In case of inverter, we know when input goes from 0 to 1, the output goes from 1 to 0. So the time difference between when the input rises to 0.5 volts, 0.5 and the output falls to 0.5, this time difference will be called the rising propagation delay. Similarly, the time difference between the time input falls from 1 to 0 and reaches 0.5 and the output rises from 0 to 1 and reaches 0.5, this time delay is called falling propagation delay. And the total average propagation delay will be the average of rising and falling propagation delays. The rise time is the time required for the output for crossing 0.2 volts to 0.2 times VDD to 0.8 times VDD. That is, here we have 0.2 times VDD and suppose here we have 0.8 times VDD. So this time is called the rising time. And again, falling time is the time required for the output to fall from 0.8 times VDD to 0.2 times VDD. That is, the time interval over here is called the fall time of a particular inverter or a particular CMOS circuit. Another thing is called contamination delay. The definitions of contamination delay is almost same as propagation delay. That is, input raising the output crossing VDD by 2. Again, from input to falling output crossing VDD by 2. The difference between propagation and contamination delay is propagation delay is the maximum time required for a change in input to bring about a change in output. The maximum time needed for a change in input to bring about a change in output is called propagation delay. But contamination delay is the minimum time an output keeps the value of previous input before it changes to a new output, or it adjusted to a value of new to a value responding a new set of input. That is, the minimum time that an output holds the value of previous input is called contamination delay. The rising contamination delay is from when input to rising output at VDD by 2. Falling contamination delay is when output falls from 1 to 0 by a margin VDD by 2, and total contamination delay is the average of rising and falling contamination delay. Here there is a mistake, here it will be CD, contamination delay, not TPD. Now inverter delay, we see they are time dependent, and in order to solve them we need to solve differential equations, which solving by hand are too hard. What we can do is we can use simulator or SPICE simulator to solve those, and we have already seen we have already solved certain CMOS circuits using DSCH, and simulators solve those equations for us and they give us the output, but they are very accurate, true, but we actually do not understand how those are getting solved. So we do not understand the basic workings of the simulator. We just provide the circuit as an input and get the delay as an output. But what we need to do, what we need to realize is how the circuit is working. And by simulators, we cannot realize how the circuit is working, and solving differential equations by hand is too difficult. So what we do is we find a way to estimate the delay. That delay will not be accurate, but that delay will give us an estimation of what the real delay is. So now we would like to estimate the delay easily. Obviously it will not be as accurate as simulation because we are using the term estimation. It's our estimate, but it will be easier to ask what if, that is, will be easier to understand how it's working. Now in order to model the delay, we will use first order RC response. We know how the RC response works. Once a capacitor is charged, it gets discharged, and the time is discharge time is called RC. This kind of response we have seen in case of step response as well. When the output falls from 1 to 0, we have seen this type of response. So here the total capacitance in the RC delay, the total capacitance will be considered C, the effective resistance in the path will be considered R, and the total delay will be R multiplied by C. It will characterize the transistor finding effective values. We will size the transistor by finding effective values or R. It will depend on average current as the gate switch. Now effective resistance, Shockley model will give us a certain value of resistance, which is not accurate for modern day transistor, it's true, and it's very complicated for hand analysis because there are a lot of parameters that needed to be considered. For example, there are mobilities and widths and lengths have to be considered. So we simplify this and we consider the on transistor as a resistor, and the value of the resistor is found using just the Ohm's formula. IDS is equal to VDS by R, and R is averaged across the switching digital gate. So this will not give an accurate result of the current, but it will help us to predict the RC delay. Again, I am saying this will not give an accurate result, but it will help us estimate what the accurate result might be. Now we want to model the transistor using RC, that is resistance and capacitance. So we are considering each transistor as an ideal switch and which has a capacitance and an on resistance. The on resistance for NMOS is considered R, and PMOS is considered twice R, and the capacitance in both cases are C. And the capacitance are proportional to width, the resistances are inversely proportional to width, as we already know that C is equal to epsilon A by D. Here A will be W by L. So W into L. So capacitance will be proportional to width, and R is equal to rho L by A. We have already known. So this A again W into L. So resistance is inversely proportional to width. Now we have known that the gate capacitance is 2 femtofarad per micrometer. It is actually this is called per micron 2 femtofarad. This is the same for source and drain, and this is applicable for width of 0.6 micrometer. As the width 0.5 micrometer, and gradually as the width decreases, the per micron decreases to 1 femtofarad per micron for 65 nanometers. And the resistance is length is 10 kilo micrometer for 0.6 micrometer processes, and as the channel shortens, as the channel length decreases to 65 nanometer, the resistance increases to 1.25 kilo micrometer. And unit transistor, for unit transistor we have already known that for unit transistor we have considered a device of 4x2. We have already seen that the width is considered 4 and length is considered 2, that is the width is twice that of length. It may be the width may be anything, it doesn't matter as long as this ratio is consistent. The width we can consider anything. We already know that the width of PMOS is twice the width of PMOS is twice the width of NMOS. This is because the mobility of PMOS is almost half than that of NMOS, and we want similar performances from PMOS and NMOS. So in case of inverter, it is designed in such a way that the width is twice the width of NMOS. Now, since in both cases the resistance or on resistance R remains the same, we want the same on resistance R. But in case of PMOSes, the capacitance would be twice C, and in case of NMOSes, the capacitance would be C. Now we see there are 4 capacitance. Why are there 4 capacitance? The 4 capacitance, one of them is source to VDD. This is drain to VDD. This is source to VDD. This is drain to VDD. Again, this is drain to current ground. This is source to ground. As a result, there are 4 capacitance involved. But these 2 capacitance are directly connected to VDD and ground, and are not involved to the switching, to the actual switching. As a result, these 2 capacitance will not be considered. Only this one and this one that are involved in switching will be considered. That is, for each of the MOSFETs, only one capacitance will be considered which is involved in switching. So as a result, we see in case of 2 back-to-back inverters, we have at the output we have 2 PMOSes and 2 NMOSes. The 2 PMOSes contain 2 into 2C, that is 4C capacitance, and the 2 NMOSes contains 2C capacitance. So total capacitance would be 2C plus 4C is equal to 6C, and the resistance of one side is R. So total delay is equal to 6RC. One thing is to be noted, that why aren't we considering the resistance of both sides and saying they're twice R? This is because either the output is 1 or the output is 0. So either PMOS is active or the NMOS is active. Since DC current does not actually flow through the capacitor, and capacitor acts as open circuit in case of DCs, we have to consider the capacitor which are active in high frequencies. But the resistance, we either consider the pull up side or the pull down side, because current only flows through one of the resistances. So as a result, total delay would be 6RC. Now we want to design NAND gate or any other gates. We want the case of ideal inverters. That is the inverter which will have twice the width, two times the width of PMOS than NMOS, to get the similar type of result. Now it is not really easy that if we multiply the width by 2, if we increase the width twice, all the circuits will give the same results as the inverter. Why is it not so? Let us look at the NAND gate design. In case of NAND gate, we have 3 PMOSes in parallel, and again 3 NMOSes in series. Pardon my poor drawing. Here we have the output node. So these are connected together. These are connected. These are connected. So this is how it works. And now it is to be noted. Now we are considering pull down side. Now, in case of the inverter, in the case of pull down, the resistance was R, and we want the pull down resistance to be R in this case as well. Now we have 3 MOSFETs in series, and we know when in series, the resistance of 3 MOSFETs will be added. Now the resistance of each MOSFET be Rm, so we'll get 3 Rm for 3 MOSFETs is equal to total resistance R, which was the case of inverter. If that is the case, our Rm has to be R by 3, that is resistance of each MOSFET has to be R by 3. If we want to make the resistance of each MOSFET 1 by 3, we have to increase the width thrice. W is equal to 3 times, because width is inversely proportional to resistance. If we increase the width thrice, the capacitance automatically increases 3 times. So as a result, we'll get the results of we'll get 3 times the capacitance, and the output would be R. Since the width is 3, we are writing the size of these MOSFETs as 3. Now let us consider the PMOS. In the PMOS, all the PMOSes are in parallel, and we have to assume the worst case scenario. What is the worst case scenario? Let us assume for pull up, let us assume that each of the MOSFET have the resistance of Rm. If all the 3 MOSFETs are switched on, the equivalent resistance would be Rm parallel Rm. We know in parallel the equivalent resistance is smaller than the smallest value. So as a result, this equivalent resistance is very low. But if only one of the PMOS is switched on, then the resistance would be Rm in itself. As a result, we can see that the resistance is maximum if only one of the PMOS is switched on, since they are in parallel configuration. And as a result, this is the worst case scenario, and we'll consider total resistance of the PMOS side is equal to Rm. Again, we know the width of the PMOS is twice, that is the capacitance of the PMOS is twice as compared to the capacitance of NMOS, and so the size will automatically be, since R is equal to Rm, there is no change in width because of the resistance, the sizes will be 2. Things will be more clear if we look at the NOR gate. Let us draw NOR gate at first. Here we have V output. At the bottom we have 3 NMOS in series, and we have 3 PMOS in parallel. Now what happens is in case of pull down network, we have 3 NMOS in series, and what is the worst case scenario? Worst case scenario is only one MOSFET is switched on for pulling down the output. If the one MOSFET is switched on and we consider that as the entire circuit, we have to consider the resistance of MOSFET is equal to R. And and again, we have seen in case of ideal inverter, the capacitance were unit sized. As a result, the size of the NMOS would be unity. Now let us consider the PMOS. Since they are in series, all the PMOS have to be switched on simultaneously. As a result, the equivalent resistance Rm multiplied by 3, because there are 3 PMOS, 3 Rm will have to be equal to R, which will give Rm is equal to R by 3. Since the resistance of each MOSFET will be 1/3, the width of each MOSFET would be 3 times, obviously, and originally width of PMOS is 2 times the width of NMOS. So as a result, total width of P side would be 3 into 2 is equal to 6 times the width of NMOS. So as a result, these would be the width of the PMOSes would be 6. Two things to be noted here. What is the what is the capacitance at the output node? The output node is connected to this PMOS and these 3 NMOS. So the capacitance at output node is 6 plus 1 plus 1 plus 1, 6, 7, 8, 9. 9. So total delay is 9 RC. So it is for you to find out what is the total delay in case of 3-input NAND gate. That will also be 9 RC if you calculate it correctly. Another thing is to be noted, the gate capacitance. What is the gate capacitance? See, we are considering that these two gates are connected, these two gates are connected, these are connected, these two gates are connected. Now this gate over here is connected to this PMOS which has a length of 6 and this NMOS which has a length of 1. So here gate capacitance is equal to 7C. This thing is to be noted. This will be useful in our future calculations. That is all for this lecture. In the next lecture, we will be learning about another delay modeling approach called Elmore delay model. Thank you.